Okay, so now if the graph is kind of congested like this, where I cannot mark the edge weights on along with the edges itself, I'll give you the graph like this, and then a weight matrix like this. So a weight matrix is kind of like an adjacency matrix where the entries indicate the weight of the edge between the two vertices. Now, this is a directed graph, so remember that. So there's an edge from V1 to V2. So I have indicated the edge weight as 3. V1 to V3, the edge is of weight 8. There is no edge from V1 to V4. So this edge is from V4 to V1. So there's no edge from V1 to V4. So that's why I have indicated that as infinity. That's the edge weight from V1 to V4. So remember that we are going to find the shortest path from one vertex to every other vertex, right? Like from the starting vertex to every vertex. So the edge weights are initially considered the path weight from the say V1 to V2 or V1 to V3. Now V1 to V4 there's no edge, so we say infinity as the estimated path weight. So we'll say the edge weight is infinity. Now V1 to V5 the edge weight is -4. So likewise for every vertex. So using the matrix you should be able to draw this edge information for the incoming neighbors. So for V1 the incoming neighbor is V4. So from the matrix the entry the edge from V4 to V1. So look at for V4 to V1 the edge weight is 2. So that's what I've written here. Now for V2 the incoming neighbors are V1 and V3. So V1 and V3 are the incoming neighbors. So in the row for V1 the edge weight to V2 is 3. Now in the row for V3 the edge weight to V2 is 4. So that's how we have to figure out the edge weight. Now for V3 the incoming neighbors are V1 and V4. So V1 and V4. Now in the row for V1 the edge weight to 3 is 8. The row for V4 the edge weight to V3 is -5, and so on. So look at the graph, find out the incoming neighbors, and then look at the row corresponding to the incoming neighbor to figure out the edge weight. So in this case for V2 to V4 look at the row for V2, and for V4 the incoming edge weight, the weight is 1. And for V5 to V4 look in the row for V5 to V4 it is 6. So that's the way you fill up this incoming neighbor information. So now we can do the initialization. So as I said, if I did not specify, you can pick the lower ID or the lower alphabet as the starting vertex or the source. So in this case I'm not specifying, so we'll pick up V1 as the source. So from V1 to itself the estimated path weight is 0. So you get all this information from this graph, from this matrix. And then every other vertex it is infinity, right? So once you get this from the weight matrix, now write down the estimated path weight on the top of the vertices as well as on the vertices also. So we are going to now go through the iterations. What we are going to do is, as usual, you use the current estimated path weights to see if you can reduce the path weight for a vertex further. Okay, so that's what we are going to do in each iteration. So for the first iteration, use the entries for initialization. So infinity plus 2, is it less than 0? It is not, so we stay with 0 and no predecessor. For V2 it is 0 plus 3 or infinity plus 4. So 3 is minimum, then infinity, so less than infinity. So we make 3 as the estimated path weight and V1 as the predecessor. Now for V3 you have V1 with 0 plus 8 compared with infinity plus -5. 8 is minimum and is less than infinity. So we make 8 as the estimated path weight and V1 as the predecessor. Now for V4 you have infinity for both the incoming neighbors. So basically we cannot reduce it further, stay with infinity. right? Because infinity plus anything is still going to be infinity, so we cannot really change. Now for v5 it is 0 for v1 plus negative 4, which is negative 4. Then infinity plus 7 is still infinity. So minimum is negative 4, and compared with infinity is minimum is negative 4. So that negative 4 is less than infinity. So we make negative 4 as estimated path weight to v5 and make v1 as the predecessor. So now what we are going to do is use these values to update the estimated path weights for the vertices and then continue the process. Just go through again for each vertex the incoming neighbors, the estimated path weights plus the edge weight. So a very simple thing. So for v1 it's still infinity for v4, so we cannot reduce it further from what we know. But for v2, v1, v3 are both not infinite, so we have to check. So 0 plus 3 compared with 8 and 4, 8 plus 4. So 3 compared with 12, 3 is minimum and the same as the 3 that we know currently. So stay with 3 and v1. Now for v3, v4 is still infinity, so we have to just check with v1. So 0 plus 8 is same as is 8, so we just stay with 8 and v1 as a predecessor. For v4, you have both incoming neighbors with some finite values, so you have to check. So 3 plus 1 is 4, negative 4 plus 6 is 2. So the minimum of 4 and 2 is 2. And it is less than infinity that we know. So we got the 2 through v5. So that is v5. Now for v5, the minimum of 0 and negative 4 is negative 4 and 3 plus 7 is 10. So which is negative 4 is the minimums and which is same as this negative 4. So stay with v1. Now as we do this, now let me tell you how to optimize the number of iterations. Keep track whether at least one entry in this estimated path weight vector changed. In this case, yes, so at least this entry changed for v4, right? So which means we are learning a better path to at least one vertex. So that means we have to go through one more iteration, right? Because using that better estimated path weight, we could optimize or reduce the path weight to some other vertices. Okay, so remember this. So when we look at an optimization example, we'll make use of this observation. Alright, so again just write the numbers on for the vertices for the estimated path weights and just check. So for v1 again it is 2 plus 2 not less than 0, so stay with 0. For v2, 0 plus 3 compared with 8 and 4, 3 is minimum, same as this 3, so stay with v1. Now for v3 you have 0 plus 8 compared with 2 plus negative 5, so negative 3 is minimum and is less than 8. So you see here, that's what I mentioned. So for v4 we are learning a better path. Instead of infinity, a path of weight 2. So using that new path weight, we are trying to see if we can reduce the path weight for some other vertex, which is v3. So 2 plus negative 5 is negative 3, less than what we know currently for v3, which is 8. So make negative 3 as the estimated path weight for v3 and v4 as the predecessor. So instead of v1, the predecessor now to reach v3 is v4. Now similarly, now let us check for v4. It is 3 plus 1 compared with negative 4 plus 6. The minimum is 2, which is negative 4 plus 6, and the same as this 2, so we do not change that. Now it is for v5, 0 plus negative 4, which is negative 4, 3 plus 7 is 10. So minimum is negative 4, so compare with negative 4 is the same as with predecessor v1. Now at least one entry again changed, which is this v3. Path weight reduced from 8 to negative 3. So we have to check if some other entries change in the next iteration. So again, write down the numbers for the vertices and do the calculations. So now V1 is not going to change because 2 plus 2 is not less than 0. Now for V2, it is now 0 plus 3 is 3, negative 3 plus 4 is 1. So the minimum of 3 and 1 is 1, less than the 3 that we know currently for V2. So we can make this 1 and make this V3, that from where we got the 1 is the estimated path weight. So V3 is the predecessor now for V2. Similarly, now V3 0 plus 8 and 2 plus negative 5 is negative 3 is the minimum and the same as the negative 3 that we know currently. And likewise for V4, V5, the entries will not change. So in this example again, we see that we have to go through all the 4 iterations, and in each iteration some entry changed. So we kept on going through the iterations until the last iteration or the last required iteration. Alright, so we can again find out the predecessor. So let us do this one more time. Say this time from V1 to V2, we have to find the shortest path. So from V1 to V2, so just look at the last vector, the last iteration. For V2, it says the predecessor is V3. So to reach V2 from V1, we have to first reach V3. So V3 is the predecessor. So now we need to know how to reach V3 from V1. So we have to look for the entry for V3. It says the predecessor is V4. Now we need to know how to reach V4. So look for entry. So for V4, it says the predecessor is V5. So V5 is the predecessor. Now for V5, it says V1 itself is the predecessor. So it is V1. So if you put together the edge weights, it should add up to what is estimated path weight to V2. So negative 4 plus 6 is 2 plus negative 5, negative 3 plus 4 is 1. So the estimated path weight from V1 to V2 is 1. Now you may also think, should we go through all the intermediate vertices like in this case? Need not be, depends on the destination you're looking at. Say if you want to go from V1 to V3, again the property that we just went through for Dijkstra in the earlier class will be applicable here. The subpath of a shortest path is the shortest path. So if from V1 to V2, this is the shortest path, the shortest path from V1 to V3 is going to be V1, V5, V4, V3. And the shortest path weight is negative 4 plus 6, which is 2, plus negative 5, which is negative 3. So that's the shortest path weight from V1 to V3. And the predecessor is V4. We have to reach V4 to reach V3. Similarly, V1, V5, V4 is the shortest path from V1 to V4 of weight negative 4 plus 6, which is 2. So the property that we went through for shortest path earlier is applicable here even for directed graph. The subpath of a shortest path is also a shortest path. Okay. So any questions? Let me save this video in a minute.